Okay, a few things. I wanted to, first of all, I wanted to clarify one point, and I wanted to talk a little bit about a couple of the problems that I've put out for you, and I'm open the floor to questions about any of the homework problems. And I wanted to discharge a couple of obligations, or a remark I made about GADTs. I want to show you what I meant, because it became clear to me from discussion that it wasn't very clear what I meant. Okay, so one thing I wanted to mention, there is a possible terminological confusion. People use the words in different ways, and so I wanted to point out something. I was saying that in extensional type theory, ETT, is characterized excuse me, by the idea that if you have a proof of identity, then you can judge that M and N are equal. So that was equality reflection or identity reflection. Okay, was written like that. And then I had something which I called uniqueness of identity proofs, but I think other people may use the same phrase in a slightly different way, so I just want to mention this. So this was to say, if you have any proof at all of M and N, then that proof has to be reflexivity. So this, excuse me, this is saying, I called this UIP, I don't know, so, but maybe not everyone calls it. You could also call this a discreteness axiom, because it's telling us that the only paths of any kind between any 2 points in A are self-loops given by reflexivity. And notice that, as I mentioned before, the rule, it doesn't even type check, so to speak, unless you have identity reflection, because otherwise you're talking about something from M to M here, and P is from M to N, so what does it mean to equate them? Well, you need to do this. And that's to be contrasted with a different principle, which says that the path spaces are contractible, and that's a different thing. Okay, so we can call this contractibility, which says if you give me two proofs of an identity, of the same identity, let's call that Q and P, then those two things are themselves equal. Now there are different ideas of what that could mean, but one possibility would be to have some kind of equality judgment like this. Let's say IDA. Okay, and that's like a different thing. Okay, this is saying that the path spaces are contractible. If you look anywhere, this is what is going on here. If you have any two paths, sort of P and Q, between M and N, well, those are in fact equal. There's only one. Okay, that's what that is saying. It's not demanding that the only paths in the space be reflexivities. Remember, I always have this difficulty of drawing a reflexivity, because really I ought to do nothing at all somehow, right? But anyway, it's kind of conventional to make a little loop to like indicate that it's a reflexivity or an identity. And so that's a different notion. So I'm allowed to have paths between M and N, but any two of them are equal. Here, I'm not allowed anything except the self-loop. So it's discrete. So that's what makes it a set. Okay, in the sense of homotopy theory. So, so that's just to clarify. So various things went around the room that I didn't fully understand, and it's like terminological problem. Okay, because some people call that UIP, and I can understand why. Okay, you know, what can I say? So it leads to some confusion. So I just wanted to make sure that we make sure I clarify that point. Okay, so another thing I wanted to mention is I made some remark about GADTs, which I think was not well understood. Okay, and I simply want to give you the gist of it without going into great details. If you don't already know anything about GADTs, well then I'm sorry, I'm not going to give you an introduction to GADTs. So I'll just tell you what I was thinking. If this is meaningful to you, good. If it's not, well, I'm sorry. Okay. So there were two things that I was saying about GADTs. One is a kind of hacky thing, use of types as data. This is a very hacky thing. And the other thing is some crazy thing about equational something or other, propagation, which I'm claiming if you formulate these things in the context of a dependent type theory. You don't need anything special. It was already there for the last 40 years. Okay, so this is what I want to do. So the example that people use, modulo notation, one of the well-known examples is you do something like this. You have a, what notation did I use? Let me just double check. Okay, so you have some idea of, so if you want to avoid these kind of things, you have an inductively defined type called ty because you're doing an eval for a programming language. And your idea is that ty is inductively defined. It's essentially a data type. Let us say for discussion it's either int or bool, just for this particular discussion. And I mean it to be inductively defined. Okay? And then you have a family of types which takes an expression of type A and gives you back, let us say, a value of type A. Okay? And eval wants to have a type that looks like that. And the whole falderall about GADTs is basically comes down to this. Okay? That's what it is. So what I'm saying here is, first of all, with respect to point one, you know, you can do some hacky encoding so that your object language types, maybe if you're lucky and are doing a simple enough object language, you might actually be able to pretend that they are, you know, treat them as data objects as being type constructors in the language you're writing this in, but anyway, it doesn't really make any sense. Okay, so it's a kludge. So what you want is an inductive type, which is the types of the language you're analyzing. And the expressions are an inductive type, which are the ones of the type A, but not the type of the programming language, but the type of the language you're analyzing, and you want a value of that type. So this is, I claim, the thing that you want. Okay? So when you write eval, what is it going to look like? Well, this is the thing. What you do is you say, well, you'll take in A as a type, and this is what goes on with GADTs. And what you're going to do is you're going to do a case analysis. So I'm going to say, I'm going to want something which ends up looking to have this type. And the way it's going to work is it's going to dispatch, okay, whatever your notation is, it's going to dispatch on what A is. So A could be either int or bool in my very trivial example here. So we do int or bool. Those are the two things. And then what do? Well, I write a function that takes in, and now this is the important point. The branches are allowed to have, so to speak, different types because that's the dependent limb. So here I would say I take in an expression of type int, and now I do whatever it is I'm supposed to do. I don't particularly care what goes here. Okay? What I care is that the type of this is expression of type int, arrow value of type int, because if you're going to evaluate an expression of type int, you expect it to deliver back a value of type int. And here you write something that looks, if you think of this as an if then else, it looks like a value of a different type, expression of bool, okay, and then whatever code you write, I don't care, that's not important for my example. This should have type expa bool, arrow val of bool, of course. And if you had more types, you would have more cases. But the crucial point is, look at the dependent typing rule for case. It'll have a motive. And the motive in this case will be, the motive that we'll use will be essentially A dot exp of A arrow val of A. And then when you're doing a case analysis, when you're in this branch, you specify the motive to be A. So this guy has to be int here, so it has to be, I'll write I here, and it has to be exp bool, I'll write B here, val of B here. And if you satisfy both of those things, then the entire body has type exp of A arrow val of A, because that's the dependent elim rule for case. Voila, we're done. There's nothing to say. It's just type theory. There's no equational propagation. There's no falderall about unification. There's no nonsense whatsoever. It's a complete, straightforward thing in dependent type theory. The crucial point is the type of the branches specializes according to the branch you're in when you have dependent type theory. Period. That is the entire semantic issue. Everything else is a kludge and a hack that works with somebody's body of code, you know, whatever. Okay, and I'm all in favor of pragmatic things, which is fine. But conceptually, there's nothing there. Nothing. Okay, and so this is what is really going on. So that's what I meant by that remark. Okay, and how the dependent elim deals with the problem and always has in a direct and clean way. Okay, make sense? Okay, good. All right, so now you know. So don't be conned by GADT stuff. All right. So that's one thing I would say. Okay, now I wanted to say something about Church's thesis. So I define Church's thesis to be the following proposition. It expresses or internalizes the idea that all the functions in type theory are computable, because they are. Okay? Everything that we do in type theory is governed by computational principles, and the only way you can ever write anything down is to say something that's computable. That's true. However, the theory does not understand its own computability. That's what the refutation of Church's thesis is about. So the statement would be, for every function from n has an index, e, and then sometimes people, I realize, writes this in different notation. Sometimes people say such that e tracks f. That's something you will see. Sometimes you will see the forcing symbol used. E forces f, that sometimes is used. And what I did is I just spelled it out to what that means exactly. What that means is for every x in n, there exists a y such that, and then I gave you this thing about Kleene T predicate. But the gist of it is, right, that what happens is if I take the program E and I run it on input X, the Y represents a trace of that run with the property that, and now this is what's key, is that the upshot of Y, the answer, you can look at that as the answer of the computation, is going to be f of X. Okay, so that's the critical thing. So this or this or this all mean the same thing. Okay, I'm just like spelling that out. Okay. And now what I was saying is, I asked you as an exercise, is refute Church's thesis. So the theorem is, it is not the case. Okay, it is not the case. Now it shouldn't be surprising at all. In fact, I find it personally, I find it amazing that people think they want to add this to various kinds of type theories or versions of logic, and I don't understand why. Okay, because it's analogous, as I mentioned to you before, if you've studied first-order logic, it's analogous to the Löwenheim-Skolem theorem, which says if a theory has an infinite model, it has a countable model. So that means even though you think you're talking about sets or real numbers with all sorts of crazy cardinalities and who knows what, really it only has countably many elements. And you don't want to be putting an axiom in the theory that says there are only countably many reals. I mean, it would be crazy. Okay, why would you want to do that? Well, by the same token, I don't want the theory to understand the computability of its own maps. Okay, it doesn't know that, so to speak. So what's going on here? So let me show you what happens. So if we apply, so what we do is we suppose Church's thesis, and then we apply the axiom of choice. That's why I put this in. So when we apply the axiom of choice, we can rotate out this quantifier. So what we'll have is there exists, I'll write it capital F, which takes in functions from n to n and gives back a number, because the for all E becomes an exist for all, okay, such that for all F in n arrow n, right, for all exists, right, that's what I did before, becomes an exists for all, right, so I do this. So this is the choice function. So this is our choice. This should start to make you suspicious now, because what is this choice function doing? Well, what it's doing is it's taking a function in extension and finding a program for it. Oh, that should be very worrisome, okay? So it has the property that for every f in n, and then we can write it out, that f of f, let's say, tracks f. Okay, just so that I don't have to write that all out again. Okay, so tracking f means, when you run it with your evaluator, you'll get, point for point, you'll get the output that you're supposed to get. Okay, that's what that means. Okay, so that's the definition. That's a result of the axiom of choice. So what we now are going to get from this now is we can observe, as it follows from this, that f of f is equal in n to f of g if and only if f is equal in n arrow n to g. So in this direction, it's trivial because it's just equality, it's just congruence. In this way, we're saying f is injective because they're tracking the same function. So it's an injection. So now there are different ways of saying this. One way to say this is that, oh, I see, I have an injection from n arrow n to n. That should make you very suspicious. An injection from n arrow n to n. No. You can carry out Cantor's argument and show that there is no such injection. Or another way, it amounts to kind of the same thing, is I've now given you a decision procedure for equality of functions on the natural numbers. What do? I compute their canonical representative using the choice function and compare them as numbers. And then you say, no, you can't do that. That's true, you can't do that. Okay? You can actually prove in the theory that this equality is not decidable. Okay, so you're not going to be able to do that. So either way, I mean, it's the same argument in either case, but that's what it amounts to. So therefore, Church's thesis failed. The assumption that Church's thesis holds leads to a contradiction. And I claim that's a feature, not a bug. I mean, that's a good thing. Okay? Yes?
Was our initial goal to find a proof in the theory of not CT?
Yeah, exactly. Yeah.
Okay, and have we done that? Do we
have
a term that witnesses?
I'm sketching, but you can do all this. Yeah. I'm sketching. Because I have to then carry out Cantor's argument and stuff, and you just have to believe me. Because you can do it yourself. I'm saying it's not hard. I've given you many, now this is plenty of hints, okay? You can write down that program. Okay. So, and I claim that this is a feature, not a bug. That's the opinion part. Okay. So this is a very good thing that it's not the case. However, you will see discussions in the literature. I was just noticing by reading something during the break that somebody was making a big deal about something or other, and it hinged on the fact that Church's thesis was refuted. And I was like, well, I don't know why you think it should hold. I mean, to me, it's crazy. Why? In other words, why should you claim there are only countably many functions? So what makes type theory work as a theory of mathematics is that it's just as rich. You know, there are uncountably many functions from n to n, and the theory knows that. So working inside of it is like doing ordinary math. Okay, everything is there. If you somehow cut the damn thing down so that it even knew of itself that there are only countably many functions, it would be horribly not like conventional math at all. Okay, so the only reason the whole thing works is because this, so to say, is because this is false. I mean, it better be false. And so I think this is maybe not so widely understood. But anyway, that's the sketch of the argument. I owed you that. I gave you that as an exercise. It struck me that few, if any of you, figured that out, or did you? Did somebody figure this out? No, from discussion in the corridor, I got the impression everyone was noodling around about T and U, and I kind of knew that that was not really the important point. So. Well, yes, they are, because yes, exactly. The fact that it tracks a particular function F is important. So you do need to know that, yes. But the particular details of what T and U are is not that important. It's simply that it means run the program and it's going to behave like F. Okay? And so that's the point. So anyway, so that was what I had in mind when I posed that as a question. Okay, so that's what I say about Church's thesis. Internally. Okay, good. So now other questions about other assignments I couldn't. Yeah.
About your lecture of that time, a question about your last lecture.
About my last
lecture.
Oh yeah.
So you've shown how we can do things in topology by using IDs from type theory. And my question was, is there, in the other direction, things we can learn about programming languages that come from this higher dimensional study?
Maybe. Maybe. My colleague Dan Makata and I are developing some ideas in this direction, but it's I'm not sure that I really want to sketch them at the board. It's going to take me a while to set them up and motivate them. Let me give you a brief flavor. It somehow recalls a little bit what I was just doing with GATs. what we were interested in doing, just to give you an idea, we're interested in looking at families of types indexed by context. We write them psi, where these are supposed to be the variables that occur in the expression. So I'd like to keep track of what are the free variables. I want to think of it as I want to write programs that manipulate expressions that have known specified free variables in them. So these are little contexts. Okay? So this is a family of types indexed by a type of context. So the idea is if psi is a context, then exp of psi is a type. Okay, that's the idea. And so what we're doing, where one of our ideas comes in is you can treat the structural properties of the context, like exchange, as an example, as a principle of equivalence between two contexts. So that you could say, for example, there's a proof, there's an identity exchange, which is an element of identity type on context, between, let us say, maybe psi with x and y and psi with y and x. And then the J rule, or the subst rule, induces you can lift this path between these two contexts as a renaming operation on exp. And it works for structural properties. Where this idea breaks down is what we really need is something more general than homotopy type theory. We need directed homotopy. We need to have the idea of paths that are not reversible. And the reason is we would like to also have things like weakening, which is not reversible, which says you can have an identity. Well, it's no longer an identity. You need a Hom. And you have a Hom between psi and psi with x, let's say. No, it's not. Well, you can call it subtyping. It's just that the structure on the higher dimensional structure is no longer groupoidal but categorical. So it's kind of subtyping, but not exactly, because it comes with evidence. The way in which you weaken matters. The way in which you exchange, which two you exchange, matters. We'd like to put this in a larger context, psi prime, right? Okay. Which ones you're swapping matters. This is relevant. It's not just a subtyping relation. So that's an idea. And we've carried this to a certain degree. Right now we're having difficulty understanding the undirected homotopy. That is like bleeding edge, even in homotopy theory. The homotopy theorists are interested in it because when they're doing like space-time physics, they want to have the idea of irreversibility of time. They want to have the idea that you can go somewhere but you can never come back. Okay, so they're looking at the undirected case for that reason. We have other more pedestrian reasons for looking at the undirected case. But that would be a kind of an example of the kind of thing that might happen in a programming context. But otherwise, it's really the situation in my mind personally is like it was in 1980 when we first were doing constructive type theory. It's too beautiful. It has to be good for something. Okay, so we'll figure out what it's good for later. So that's a bit of an article of faith. Okay, so that's my own personal belief at the moment. But if you have ideas, you're all ears. Okay, for doing this. Okay, other questions about other assignments I gave you? Or previous lectures before I do anything else?
Yeah? Yeah, there's a question.
Oh, sorry, yeah, thanks.
About OTT, the identity types and their inhabitants are defined by conviction of the structure of the type.
The identity types and say it again, please. Sorry, it's my fault.
It's about the definition of identity types in OTT. It's identity types in type A is defined by induction on the structure of A.
That's in OTT. That's the way OTT works. That's called the setoid interpretation of vector.
And I'm not sure I understand correctly, so maybe to clarify, you please define the identity types of natural numbers themselves.
You'll take that as a primitive. Or if you have a general notion of inductive type, the way you'll define that is inductively. You'll say 0 is equal to 0, and if m and n are equal, then so are their successors. and you'll take the least type, it's an inductive definition of a type, it'll be the least type closed under those two conditions. That's what you would do, okay? So in a setoid interpretation, the setoid associated with the natural numbers is exactly that one. And so that's what you would do. So I didn't really spell that all out fully because I felt other things were more important. But if you look, there's papers by Alton Kirk and McBride and probably other people who have written all about this, and you can look, and the buzzwords are setoid and observational type theory, and if you Google for those, you'll find them. And you can get all the details there. Other questions? Yes?
Is there a relation between ET and singleton times?
There must be. Yeah, I don't know. I don't know. I don't have an answer for you. You're good at asking questions, but I don't have an answer for you. Hey, don't all be so quiet. Are you just tired?
We
want to hear about. Yeah.
We want the finale.
Yeah, the finale.
Yeah.
Last question before the finale. At one point you said that saying prop versus type in the platformer was largely a matter of perspective.
Was what, sir?
Largely a matter of perspective.
Yes.
Yeah. When you go to polymorphism in the unpredictability.
Okay, so this is something I'm going to get to next.
Okay.
The word, okay, this is another terminological snafu. Okay, various terminological traditions keep colliding as these various fields come to learn about each other and mix and match and stuff. So there's another interpretation of prop which is connected with universes, which I'm going to talk about. So that will be a good jumping off point. Okay. Good. Yeah, because interesting things are happening in this space, and I have some. Surprisingly enough, I have opinions about how they're going to play out, and I'll let you know what they are. Okay, so let's see. What do I want to say next? Let me think about this for a moment. Okay, so. Okay, were there other questions about anything that I did in my first whatever number of lectures? I mean, that's perfectly fine to ask. Okay. All right, so let me say then, okay, then let me press onward a little bit and say a few things. So there are two topics. I mean, Steve, I think, will talk about some of this stuff in more detail. So, and I certainly do not have time to really develop everything. But there were two topics that emerged from what we, well, let me first of all say, the first thing we observed is that there was this higher, what is called the higher dimensional structure in type theory, in ITT, let's say, okay, given by, I'll write it as like iterated identity types. This is a good way, iterated identity types. This is a good way for you to like remember like what this is all about. So we started out with a basic idea, like identity at some particular type A between elements of M and N. So that would be sort of our first dimensional structure, okay? And so what we can do is so that's the first idea. And then we had proofs, P of such identities. Okay, so that's the first dimension in some way. And then we found that if we had two such things, let's call them P and Q, we could then extend that notion because this is a type, and so it, of course, has a notion of identity as well, right? A particular A is that identity type, so we'll look at the identity type at the identity type. That's like you don't think of it right away, possibly, but then it gives you the ability to talk about the identity between P and Q, which are proofs of identity of M and N. And so we're going to have proofs of these, and we could call these alpha and beta. Okay, and then very shortly I start running out of creative new letters to write, but we're going to have some other kind of even higher identities, I know it gets a little crazy, right? So this will be between M and N, this will be between P and Q, and this will be between alpha and beta. And pretty soon it becomes rather hard to write it all down. But you can see the structure, I hope, of what's going on. And the picture we draw is, you know, we have maps, M and N, and then we have proofs, let's write it like this, relating them P and Q, and then we have proofs relating those like alpha and beta, okay? And there's this infinitely descending or ascending, depending on your point of view, structure of relationships between these things. That's the idea, okay? That's how this works. And so, and this just goes on forever, okay? The structure can be extended as far as you like. For various technical reasons, like, for example, Dan Licata and I have studied a two-dimensional type theory in which we cut it off here. And what does it mean to cut it off there? It means to demand from this point on UIP, that everything is discrete from that point upward. So in particular, the groupoid axioms are satisfied exactly here, but only up to higher identity here. Okay? So you can cut it off at any level you want, and that's called the N truncation, is when you truncate the theory at level N and make everything be strict equalities from that point onward. Okay, yes? If you do it all, it's a weak notion. If you do it all, the reason it's weak is because what I haven't displayed here, but I'll remind you of, is that there need to be equations, okay, to make the whole thing work out. For example, if I take P and then I take P inverse, I want to relate that to the identity. Now, one possibility is to demand that they be equal, and that would be a strict interpretation. But another possibility is to simply say, no, they're deformable. That there's a cell here, a surface, along which I can deform that composition into that composition. And that would be called maybe alpha. Okay, there would be a deformation. Of course, the alpha itself has inverses because it's symmetric and transitive. So it itself would have to have further deformations in higher dimensional structure to witness its well behavior to form the structure of a groupoid. Okay? So that's what we're talking about. That's what weak means. So this is the raw structure, if you will. This is the stuff that comes out. And this is the relationships that have to hold, which can hold either strictly, which means equality, up to equality, or sometimes people use the phrase on the nose. And weakly means up to homotopy, up to higher deformation. Okay, and that's the thing that people are interested in. And if you have them weakly all the way, that you make no strict requirements whatsoever, that's intentional type theory, and it has this infinite dimensional structure. Okay, that's inherent.
When you cut it off, when you say equality, it's technical equality you're referring to.
Yeah.
Okay.
Right there. So that's the first observation, is that there's this higher dimensional structure is present. Now I can make a remark, which is, if you were only ever doing set theory, it means you were only working at dimension 1, ever. You were truncating from that level on. So we have this curious state of affairs that has been going on for a couple of decades, that people have been doing set theory inside of ITT, homotopy sets. They've been working with discrete sets only, but paying all the cost of using higher dimensional structure without exploiting it. This is the explanation for why it is so painful to work to do formalizations of set theoretic mathematics, homotopically discrete mathematics, inside of calculus and constructions, because working with ITT is a humongous pain in the ass. And the reason is you're paying the price of higher dimensions without getting any benefit. Whereas New Pearl, we can now say, this is a retrospective thing, was always one-dimensional and admitted it outright. That is what extensional type theory in the form I gave you was about. That's why it is much easier to do set theory in Perl than it is to do it in Coq. And that's why people who do mechanizations, say there's been a lot of push to put more and more kind of extensionality into the type theory because it's too painful to pay the price of higher dimensions if you're not actually using them. It's only in the last year or so that there's been the opportunity to actually exploit the higher dimensional structure so that at least the suffering is worth something. So that's the way I would describe the situation, how it has been, and that explains a lot to me, like about these kind of disputes over many decades about the formulations of type theory. So there's more coming up, but anyway, I wanted to mention that. So that's a nice way to situate, to understand where everybody's been standing and how it all fits together. So that's a good thing. Okay, so this higher dimensional structure now can be exploited in a couple of ways, and I'm going to talk about two ideas in brief, okay, that really take advantage of the higher dimensional structure. And partly this is a recap and partly it's not. And the second one will address long-standing issues, at least for me, long-standing issues in the semantics of type theory are finally being addressed in this framework. So the two main things that have come so far in my mind are what are called higher inductive types, or hits, and the other thing is the univalence principle, univalent universes. Univalence, I'll just say univalence. I'll get back to that in a minute, okay? So the idea about higher inductive types is that I was mentioning very briefly this morning, some of you are maybe acquainted with the idea of presenting algebraic structures by giving generators and relations, okay? What happens in higher inductive types, so the idea is you say, here are a bunch of generators, close them up under the algebraic laws, and you may get some additional equations. So, for example, you might demand, if you're having a group generated by a particular set, you might also have the relation, some particular words, some equations that you wish to hold in addition to the ones that follow from the group axioms. So that's a method of generators and relations for generating free structures on the specified data. In higher inductive types, what you get is generators and more generators. You don't need relations because those relations are specifying equations, and the way I specify equations is as generators at a higher dimension. This, to me, is a very beautiful idea because it subsumes quotients, it subsumes truncation, squashing, proof irrelevance, lots of things that have been studied in type theory over the last 30 years, all come down to just one thing. It's a very nice thing. But I'll warn you, this is a bleeding edge concept. Okay, this is like the whole type theory of this has not been worked out. So from here on in, it's bleeding edge. Okay, so be warned. Okay, not everything is completely worked out. So I mentioned to you before, perhaps the best starting point is we have the interval, we have 0 and 1, and then we specify a segment, which is a proof that identity on the interval 0 is, so to say, equal to 1. I would rather, in the same way that I've often said, psychologically it's easier to think of that as a path between 0 and 1. It's a little weird to say, okay, it's the Booleans such that the two Booleans are equal. That is what I'm saying, but it's a different, I don't know what to tell you. It may feel better to think of that as a path. That's the right way to think about it. So we're specifying as I mentioned before, the picture is we have 0, we have 1, and they're linked by a segment. Okay, so that's an example of a higher inductive type. What can you do with a higher inductive type? Well, what you can do is the elim form is two-dimensional. Because what it does is it tells you on 0, you send that to some x, 1, you send to some y, right? Because like an ordinary inductive definition, if I didn't have this, that would be an inductive definition of the type with two elements, 0 and 1, so basically the Booleans. And the way you compute with that is you say, well, here's what you do with 0, and here's what you do with 1, and that's your map. Well, now in addition, I want to do something else. I want to send something, the segment, which is witnesses that 0 is equal to 1, let me write twiddle, and I want to send that to a path in the space, in the target space. So these are going to be in some type A. So what I want to do is I want to send that to a path between x and y and A. So the elimination rule will do this. The elimination rule is two-dimensional. If I had a three-dimensional type, it would have 3 dimensions. So you have this multi-dimensional elimination that lets you give an inductive definition that tells you what to do with the generators at each dimension. Okay? And then because it's the least type generated by those generators, then if you specify that information, you've specified the mapping. It's like an initial algebra. Okay? That's the idea. So there should be some kind of infinity initial algebra structure should come out here somewhere. Okay? I don't know of that having been worked out yet. Okay? But there's a feeling about this. Okay? That this is how this should work. So a similar thing happens with the circle. If I take the base point in S1, and then I take the loop, which is, well, we'll just write it B twiddle B. I'll write it like that in S1. I mean the identity type, but it looks nicer to think of it as a path. So pictorially, as I mentioned before, you have the base point, and you have the loop. So what does it mean to elim from that? Okay? Well, what I do is I send the base point to some point x in the space, and I send the loop to a path, P, that goes from x to x. It's a loop in the space. This is exactly, if any of you have ever studied any algebraic topology, that's the very first thing you do. You get some idea about the structure of a space by throwing out a lasso and seeing if you can tighten it. Okay? If you can tighten it, then it doesn't have a hole in it. Okay? So that concept can be expressed by looking at, there's a group structure associated with the paths given by the composition and so on, and you want to look at the structure of that group. Okay? And the structure of the group tells you about the structure of the space. That's how it works. So this is the idea. It's just an inductive definition, whereas at dimension 1, dimension 2, you send B to some point in the space and loop here. So you have some space A, you identify some point X, and you identify some crazy path that goes from X back to itself. Then it becomes interesting when looking at all such paths to discover whether they're contractible, in particular, whether this space can be contracted down to the identity, in which case there's no hole there. Okay, that would be an example of how that kind of reasoning works. Yes?
Say again, please?
How would we discover that?
How would you, I'm not going to do this. There's a construction called the fundamental group, and you look at the structure of the fundamental group. So, and here we would end up saying the fundamental group is trivial. Whereas if you're on a circle, and if I throw a lasso around the circle, you can't pull it tight because the circle is not a disk, it's a circle, and a hole in it. You can't pull it tight. The fundamental group is Z. It says you can go around, and you can go around, and you go around like this. And the proof that this amounts to Z is the winding number, which is basically just it's a canonical form. So what you do is you say, if I have a path that goes like this and then goes back like this, you just cancel it. And then at the end, you're going to be either going around 0 times, some negative number of times, or some positive number of times once you've canceled out the redundancies. That's a good old normalization procedure that functional programmers would love. That's how you compute the fundamental group of a circle. And then you prove that it's Z. Meaning, it's the winding number. That the path space on the circle is characterized by an integer telling you how many times you go around. End of the discussion. That's the whole circle. Okay? And it's just functional programming. Yes.
What are the uses of the unit and the circle type in functional programming?
What again, sir?
What are the uses of the unit and circle type in functional programming?
I don't know.
So they are only mathematically interesting.
What's that again?
They are only interesting from a mathematical point
Yeah,
of
we
view.
could dispute the only part, but yeah.
Can you give an example of a higher inductive type that's useful from a functional programming point of view? For example, can you use it to define the rationals with the quotienting equality on it? So that you define the rationals as pairs of 2 integers such that, and add additional equalities such that
It should be possible if it's characterizable as a free algebra, then you can do it, yes. Because you can just, if the method of generating the relations can be done as a higher inductive type. So yes, that should be possible.
So you can then say for all x, y
Yeah, you do the usual cross multiplication.
Yes.
And I think more simply you can do it with, you can define z from n this way by doing the exact same thing except with the subtraction instead of division, right? And you just define what equality means by subtraction. So you can get z from n by saying an integer is the difference of two natural numbers in the same way that a rational number is the quotient of two integers. So that's what you do. And I guess you could do that. I haven't really thought about it. To be honest, my head has been in this particular, this is where I've been for the last couple of years. So.
You also said that the existence of this unit type implies functional extensionality.
Yes, I can sketch that proof for you. That will come up. Okay. But I don't know if I have the time right now to do this.
Can you give the intuition real quickly, otherwise?
What, say again?
Can you give the intuition behind it real quickly?
Yes, the intuition is the following thing, is that I arrow A is isomorphic to the path space x, y, in A, x, y. Okay, that's the idea. Why? Because a map from the interval into A picks out two endpoints.
It sends 0 to here, it sends 1 to here, and it sends the segment here to a path between them. So basically, all the paths between x and y arise as the image of A. Okay? And then the idea is, if I have a map from A to I to B, that can be, by currying and uncurrying, turned into I arrow A arrow B, which is isomorphic to the paths in A arrow B. Well, this thing, this big sum, I'll just write it like that, the path space. Okay? Like that. So the way the argument works is critically like that. Because you're given, for every A, you're given a path, okay, between mx and nx, right? That's the premise of extensionality. That turns into a mapping from I into B, which picks out mx and nx and the path between them that you're given. Then you just swap these two things. That's just a functional programming trick. And now you've got from the interval two functions, f and g, and a path between them, which is the proof that they're equal. That's the whole idea. And classically, the way people do homotopy theory is that this is the definition of a path. See, in the textbooks, this is what is called a path in A. A path in A is a continuous function from the unit interval, thought of as being a subset of the real line, into A. Because what it does is it sends the endpoints of the interval, 0 and 1, to points in A in a continuous way, because the interval has the segment between it. But really, I don't care about the real number. That's just machine language. That's just hacking, okay? Forget the hacking. Let's just do an abstract type. The abstract type is that there's a segment, okay? So that's all we care about. It has endpoints and a segment. And then the type theory as general considerations ensures that the equality is respected. This is what I told you in the very first lecture. It was centrally important to talk about respect for equality or functionality. So here, as soon as I introduce the segment, everything in sight automatically respects it because of subst and resp that I gave you. So it means that maps automatically respect the segment. So then there are paths. This I arrow A are paths, and in fact you can internally define this isomorphism between I arrow A, the conventional formulation of homotopy, or path space, as this. We'll call this the path space of A. This is the big sum. It's we'll call it path in A. That's all the paths in A. You just sum them up over all the endpoints, glom them all together. That's all the paths in A. And then from that, in this observation, you get the function extensionality from the interval. That's how it works. That's a sketch, but I can only sketch in this last lecture. I don't have time to really develop everything. Okay? So when you start seeing things like this, and when you start taking apart the constructions that are going on in homotopy theory, and you realize there are functional programming tricks that we all know and love, like normalization. There are arguments that are just cut elimination. I went through this 85-page paper, and by the time I got to like page 80, I set the paper down and started laughing. It's exactly a cut elimination argument. Exactly on the nose, a cut elimination argument. Phrased in some geometric way that, you know, appeals to a different audience, but it's really cut elimination. So these things, these are not accidents, okay? So I give a lot of credit to Jean Girard because he has been saying for decades, drawing attention to the logical content of various things in mathematics and vice versa, and in particular stressing cut elimination. And I think he's quite right. That's quite right. So I think it's a... Anyway, so that's how that goes with the interval. So that's the notion of higher inductive types at a very high-level nutshell kind of thing. The main point being, it's the method of generators and generators, generators and more generators. And you can do this at arbitrary dimensions. Because how do you get like spheres and stuff? Well, you just start having, you can think of rotating, spinning things around and equating them. And there are different ways of formulating, but let's not worry about it. They just get higher and higher dimensional structure. And so you can just get more and more and more generators. And using this, you can build up a library of these kinds of geometric objects, and then you can go to town with them if you like. Okay, whether other examples come up, those are good questions. I don't know who's first.
Go ahead. I'll try and speak loudly. 15 minutes ago you said this subsumes squashing, and I'm just curious, is that the squashing from the indirection theory paper from a couple of years ago?
From the what theory?
Indirection theory.
Indirection theory. I don't know what that is.
Okay, well, what was squashing?
In type theory, we introduced in Perl the notion of the squash type, which is, one way to think about it is you take a type and you quotient it by the full relation. All elements are equal. The reason to do this is as a way of expressing proof irrelevance. If I want to express to you merely that something is true without telling you anything about the reason why, that is, I don't want the computation to depend on the reason why, then you squash it. The way you squash it is you just say, they're all equal. Since they're all equal, you can't tell them apart.
Okay.
And therefore, you can't depend on them.
Does it have anything to do with the kind of stratification that you get from, say, cryptological relations?
What kind of stratification do you have in mind?
I'm not sure.
Offhand, no.
Okay.
That's a safe answer, but I don't know if it really touches your question or not.
Okay.
Maybe we can talk about that.
Sure. Yeah.
Okay. Yes.
So usual inductive types have restrictions on what you can define as an inductive type. For
Yes.
Positivity condition as well. Does the higher inductive types have additional restrictions?
Yeah, well, there must be. And the answer is I don't know straight away. We don't really know what these things are. I'm telling you honestly. Okay, there isn't a full theory of this worked out. What you're getting at is why do I know there's going to be a free structure? Okay, and to my knowledge, this has not been worked out. So I told you this is bleeding edge stuff. You can, if you wish, regard it all as rubbish.
No, I was just wondering if there were some conjectures or.
No, we don't know. We don't know. Speaking for myself, I don't know. Okay. I mean, yeah, there has to be somewhere, right? Somewhere there's got to be some infinity groupoid structure and some kind of a functor on this thing, and initial algebra for this functor, and these generators must present one of those functors, and so on and so on. It's got to be, but I don't know exactly what that is. That's the honest answer. That's at least my personal state of knowledge. There may be other people who know more than me. So, yeah. Okay. Yes.
Is there a tidy hit that has multiple constructors for the relations?
Multiple constructors in the...
For the relation?
Oh, yeah, sure. Yeah. Oh, definitely.
Is there like a...
I'd have to think of one off the top of my head. I didn't write one down. I hate to, if I don't write them down in advance, I hate to put them on the board because I'm going to screw them up. So I'll owe you that.
Is it just any free algebra with multiple...
Yeah, you can have multiple. The reason is you have lots of generators, and then you can have various relations amongst them. I can have two different arcs between the same 2 points, and then I can decide that they're connected. That's a way of making the sphere. Okay, so that's how that would go. Yeah.
Does it know how to compute with these? Do you still have?
Well, the computing with it is what I was saying here. When you specify a recursor, I'm not giving a notation. I don't know what the notation is. But you tell what to do on 0, you tell what to do on 1, and at dimension 2, you tell what to do on 7. In the same way that with an if then else, you tell what to do on true, what to do on false. There's nothing else to do because they're only one dimension. But if you're in higher dimensions, you have to tell what to do here as well. And so that's what gives rise to this picture, because If I take the interval and I map it into a space, what I am doing is designating two endpoints and a path between them. Because I'm required to send 0 somewhere, 1 somewhere, and the segment to a path. And the path is, lives in a higher dimension. Okay, so that's why it works like that. And that's how people think. Classically, that's how people think about it. I is I or I. If you look in the textbooks, that's what they do. Okay. But from an abstract types point of view, we can apply programming good computer science principles and get much cleaner code. I can absolutely guarantee you that. It's much cleaner code. So far, that's what we've been doing. A lot of our meetings, we basically clean up, so to say, known arguments and figure out what's really going on by writing good code.
So why is it that with function extensionality you can't get canonical forms for everything?
No, you can't bung it in as an axiom. Okay, it's just a new form of identity proof. Okay, so you're saying why does the whole theory hang together? Well, that's an interesting question. Like I said, it's bleeding edge. We don't have a fully worked out story about higher inductive types. Okay, that's in all honesty. Okay, everything I'm telling you is kind of half-baked now at this point in this lecture because this is like minute by minute. Any second I could get an email about some new development. All right, everything is up in the air. So this whole lecture, at least this part of it, should be considered, entertainment only. Because we don't know, honestly. The answer to almost every question is we don't know. So we don't have a proper computational foundational account of higher inductive types yet. Okay. But there ought to be one. It makes good sense if you ask me. And so we're investigating that. That's ongoing. Yeah.
Aren't you afraid that all these extensions will blow up the type theory completely?
What about type theory?
Aren't you afraid that these extensions will blow up the theory of the type theory completely? Because currently it's still...
I'm not... It depends what you mean by that statement. Am I interested in the foundational issue of what's going on here? Of course I am, yes. Do I think that it's not possible to do that? No. I actually think that we will do this very soon.
You will do what very soon?
What's that?
You will what do very soon?
Proper foundational account of the whole thing.
Okay, but proper you also mean relatively small.
Well, I can't answer that question. Okay. I don't know what to tell you.
Well, I'm more meant, what's your definition of proper?
What, sir?
What's your definition of proper? What's your definition of proper in this case?
Computational, based on computation.
Okay.
Okay, I'm going to have a whole computational account. I am currently optimistic that we will have a proper computational understanding of the higher dimensional type theory with higher inductive types and univalence before very long. I personally, it's an opinion. That is my personal opinion. I think that that is possible. Of course, like any research thing, I could end up being wrong. So right now the justification for it is Blavatsky has constructed a model of this type theory in the categories and Puschel sets. And this is a very highly non-trivial construction. And very highly. I would say he and Murdoch are probably the only people who actually understand. Okay? And that's my opinion. And that's the justification for it at the moment. I don't consider that to be ultimately satisfactory. I would like to have a computational interpretation of the whole thing. And I kind of think it should be possible, but I may end up being wrong. Yes?
So Bob, I asked Blavatsky to remember way back. But, homotopy theory is a theory of classical mathematics, right?
Yeah, but it's not. That's the interesting thing. It's all really very constructive.
So they're really doing constructive math that just didn't fully realize.
Absolutely, in disguise. That's why it all maps into type theory in the most natural way imaginable. I find it wonderful. I find it absolutely great because I have always believed, okay, and type theory is the master theory of everything. Further evidence that this is correct. So that's the idea. Yeah, no, it's great. It's fantastic. All these arguments, they're really totally constructive. In fact, the core idea of homotopy is the idea of a path, the idea of evidence that things are related. That's a totally constructive point of view. And you manipulate that evidence and you compute on that evidence. It's a completely constructive point of view. Groupoids are equivalence relations with evidence. That's what they work with. That is a beautifully constructive idea. So that's what's remarkable. It's completely remarkable. So I think it's cool. Let me tell you what unibalance is, okay? Because nobody wants to. So that's a flavor of higher induction.
Balance is connected with the idea of universes. So first, so the question is, what it's all about is, what should be equality in a universe? So in order to explain that, I have to explain what a universe is. So I'll come back to this, but univalence is an answer to the question, what should equality mean when you're talking about a universe of types? So let me explain what I mean by a universe. So the idea of a universe is it's the type theoretic analog of a large cardinal axiom in set theory. One could say that, an inaccessible cardinal. It's somehow the analog in some sense of an inaccessible cardinal. Okay, the idea of an inaccessible cardinal is that the main engine for creating stuff in set theory is taking power sets. Okay, and the idea of an inaccessible cardinal is you can't reach it from where you are by iterating power set by anything that you have available up to that point. Okay, so the first inaccessible cardinal is omega itself. If you don't postulate that you have natural numbers, everything in sight is finite. You can build up all sorts of finite sets, and you can take power sets of them all day long, and you'll never hit omega. That's why you need an axiom of infinity. So that's the first inaccessible cardinal. Then you can start again and say, let's take power sets of power sets and 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 power sets. And then you can go to a next cardinal, the first inaccessible cardinal after that, and that extends the power as well. So what we do is that there's a kind of similar thing, which is the notion of a hierarchy of universes. So what is a universe? It's a type of types that is closed under, usually we demand that it's closed under, well, everything in sight, whatever the hell that means, okay? Okay, so this is the idea of a Grothendieck universe, okay? So the idea is this, is that it's everything to do with limitations of size, okay? So the idea is that if we start out with a type theory that we were developing during the course of my lectures, we had, let's just say for concreteness sake, we have natural numbers, and we have 0, and we have 1, and we have cross, and we have plus, and arrow, and pi, and sigma, and maybe I have various hits. In addition, that would encompass a lot of these, but anyway, I might have this, but I have various things, okay? What I can do is I can sort of draw a line, draw a circle, or sort of draw a box around everything I've done so far and call that one thing, and that's called a universe. And then I can iterate everything using a universe. So the idea would be I can introduce, let's say, we'll start with U1, yeah, we can call it U1 typical, which would be like the first universe. So the idea is we're going to have the first universe, and it's closed under everything except, of course, itself, but formation of U1. So for example, we will say n is in U1. That will be a rule. Well, U1 will be a type. So we'll say U1 is a type. N is in U1. Okay? Then we'll say if A is in U1 and B is in U1, then maybe A cross B, for example, is in U1, etc. And then with pi, we say if A is in U1 and with x in A, B is in U1, then we'll say pi x in A, B is in U1, etc. Okay? We'll make a definition like that. So at this point, all the types you've seen end up being elements of the universe U1. And then in addition, we chuck in another type, which is U1 itself, which is not an element of U1. However, U1 is an element of U2. So what you do is you say U2 is a type, and then you say U1 is a type in U2, and then it's closed under everything in sight. Okay? So it's closed up. So in particular, we can give an example. I can form pi x in U1 dot x arrow x, maybe. And that will be in U2. That would be an example. Okay? Why? Because U1 is in U2, and every universe is closed up under everything in sight. So U1 is in U2, and then everything that's in U1 is a type. So this is which is a type in U1, so their function space is in U1. And you have cumulativity, I forgot to say, which is to say that if A is in U1, then A is in U2. That's called the cumulativity. Okay, and then that way, with x being in U1, it's also in U2, and then U2 is closed under arrow, so x arrow x is in U2, and therefore everything is in U2. I needed cumulativity, I forgot to mention that. Okay, so that's the notion of a universe. Okay, so this is, and you have an infinite hierarchy of these things. This is the, okay, everything here like goes to infinity. That's part of the fun. Okay, so now we have an infinite hierarchy of universes. The reason for doing this is now I can introduce things like type quantification. I can quantify over types of the first universe. We could call these, sometimes people use the terminology, that would be a small type. And therefore U2 would be a, well, not so small type. Okay. And then pretty soon you start running out of words. So you can then have a rather large type and a, well, large but not insufferably large. And then, and you can keep doing that, okay. But anyway, you might as well just use this. So you can just bring this up. Okay, so you end up with this kind of structure, okay. So you have this U1 is in U2 is in U3, then all the way up. And moreover, I'll just use it informally, say they're contained, meaning cumulativity. Everything in U1 is also in U2, et cetera. And then they're all closed up under everything around. Okay, under all the type constructors that you want. So that's the notion of a universe. Sometimes in addition, there's a zeroth universe, which is called prop, and that is confusing. Okay? So sometimes there's also U0, which could also be called prop. Okay? And now this is a tricky business, okay? Because usually it has additional closure conditions, all unto itself. In particular, it's closed under quantification over prop. And that's the notion of impredicative quantification. That's typical. And calculus of constructions has this. The main distinction between, one of the main distinctions, apart from extensionality and intentionality, between New Pearl and calculus of constructions is, in New Pearl we never saw any need to have prop. And with the development of homotopy type theory, people now seriously question whether there's any use for prop whatsoever. In fact, my own belief, personal opinion is, this will go away shortly. Okay, this will be all gone. It's not useful, and the reason is, right? The reason is, I don't have time to develop all of this, but the reason is what justifies this is a principle of proof irrelevance. And the idea about the homotopy interpretation is the exact opposite of proof irrelevance, because the identity type, which expresses equality, cannot be regarded as a prop in that sense, because to do so would eliminate the entire structure that is of interest, namely the identification of proofs of identity with paths in a space. You don't want prop. Prop is like completely the wrong guy for this purpose. And experience in 30 years with New Pearl, we never needed prop. There's never any use for it. In that sense, we take very seriously props as types. Yes?
We also used in Coq for abstraction, namely the parts in prop are being removed. How will it happen if we drop prop Currently in Coq, we have program extraction, so given a term in Coq, it extracts to a
Because
non-level.
we have squashing. I told you, higher inductive types give you squashing. So squashing gives you proof irrelevance, so I don't need prop for this.
Okay, so you mean you can define prop
Yes,
using
which
squashing.
is what we did in Perl. We had a dedicated squash type. We didn't have higher inductive types, but we got a squash type.
Okay, and then the extraction mechanisms removes those
Yes,
squashing.
exactly, yes, exactly. Gives you proof irrelevance, yes.
Okay.
That's the answer to that question. Okay, yes?
You use these ID types for paths to get the topological object, and also for a concept of equality. But do we need to keep thinking of ID as an equality? We could just say it's just path.
Yeah, that's true. But somehow the way the whole thing works is that those should be thought of as equations. And the reason is because everything has to respect it. You know, that's the idea. It's not just some random type which I coded up. It's really baked into the theory as equality. And the reason I say that is because that way we know that the family's all respected. Okay, that's what's important. It has a privileged position. That's why I started my lecture with this week on Monday. That's why I started with this emphasis on equality. That's the reason. So it really has to be equality to make it work. Yeah.
I had another question. In my experience with predicative system is that it's painful to have to choose the universal in practice.
Yes, but there are ways to deal with that. Pollock and I had a paper about in 1987 that seemed to work very well in Lego at the time. And for some reason it's not used in Coq, and I don't know why. I'd rather not go further because I think most people don't know what we're talking about.
I know
I'll be happy to talk to you about it later. Yeah. Okay. Yeah.
Can types in prop have more than one element?
Well, usually they're proof irrelevant. You squash them together. Okay. And by the way, as a way of fixing terminology, in case you don't know, this is called unpredicated quantification. Just so you know. The rest of the structure is the opposite of that. It's predicated. Okay. You just mentioned that. So, no, I mean they're squashed because that's the point of the prop in some way. But we have other squashing mechanisms, so it's not necessary that we have that.
Is that related to the idea of minus one throughput or minus one category?
Okay, so now I get confused all the time. There's a collision of numbering schemes, and it might be that I picked the wrong number. Okay, there are some versions of this where prop comes out as -2 actually. So it's a collision of numbering. If I got it wrong, I just plead guilty. Okay. The reason is there's two traditions for how to number them, and they collide. So that's a bit of a mess.
That's not what I'm asking.
Oh, okay. Maybe you're talking about something else. Okay.
Yeah. So like in the notion of dimensions, like you have sets and then categories and subcategories, and then you can go down. Like beneath sets, there's the truth values, and I've seen those referred to as H props. So I'm wondering if that's
H prop is a different thing. That has to do with the homotropy structure of the space. H props exist in the predicative universe and have nothing to do with this prop. It's another terminological confusion. Okay, it's just an unfortunate fact of life. Okay, I can't do anything about that. H prop is a different notion. H prop comes out as -2 in some numbering schemes. Let me leave it at that. Okay, because all right, I do want to say something useful about this in the close. Okay, so all right, so let me do that. So yes, that's a different notion. So you can recover the notion of prop and proof irrelevance in this more general higher dimensional setting. I think it was a low dimensional object with a trivial, all the elements are contracted. So we'll come back to that. Okay, so here's what I want to say now. So we've defined what a universe is, so you can get a feeling. Now, what should be equality in a universe? What should be the meaning